All right. More permutations. Woo! This time we got some with repetition and we got circular permutations. Exciting stuff. So let's jump right into it. All right. So just kind of show you kind of the motivation behind this section here. Let's think about how many different ways we can arrange these letters. Let's start with Mexico. And this should be kind of review from the last section. It's pretty straightforward. Mexico, I think we all can tell that it has 6 letters. All right, each letter is unique. Okay, so in order to arrange those into quote-unquote words, okay, and these are just nonsense arrangement of letters. They don't need to be real words. All that would be is just 6 factorial. Okay, and 6 factorial equals 720. Pretty straightforward. All right, so Canada, on the other hand, has these 3 A's, all these repetitions here. Okay, so let's say I call this first A green, second A red, and the third A purple. Okay, so in general, okay, this arrangement of the letters, let's say I had like show you kind of a few arrangements of Nadaka here. Nadaka, just an arrangement of the letters in Canada. So if I treat those different A's as kind of unique things, these are different arrangements, but really they're not different words. Okay, so we need to kind of figure out a way to kind of divide out by that issue. And luckily it's not too hard, okay, because the number of ways to arrange our 3 A's is just going to equal 3 factorial. Okay, there's 3 A's, so it's very straightforward to do that. And the total number of ways to arrange the letters in Canada, once again, it's a 6-letter word, so that's just going to be 6 factorial. And then we can just divide out by all of these repetitions, because at the end of the day, these arrangements are all going to be the same. So divide out by that 3 factorial. So 6 factorial divided by 3 factorial is going to be 120 ways. Okay. So let's kind of generalize this equation here on this next slide that we did right here. Okay, so if we have, let S be a set of n elements of k different types, and like n sub 1 is the number of type 1, n sub 2 the number of type 2, etc. Okay, so this is basically permutations with repetition. So in a situation like Canada, okay, and so the total number, that n, there's total of 6 elements in our set, so that's what we got, that's 6 factorial. Okay, there's 3 A's. If we're treating that as the n sub 1, a total of type 1, that would just be 3 factorial. And then there's 1 of every other type. All right, so you don't actually need to include all those 1 factorials for the 1C and the 1N and the 1D, okay? But that's just following this formula, okay? So it's the total number of elements up top, and then you're basically just dividing out by the repeats, okay? So in our case for Canada, we divided out by the 3 factorial because there was 3 A's, okay? As easy as that. So let's take another example here. Great word, Mississippi, M-I-S-S-I-S-S-I-P-P-I. how many permutations are there of the letters of Mississippi? All right, so just following the formula, it's going to be very straightforward. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters in Mississippi. Hope I counted that right. So that's going to be our numerator, 11 factorial. And then we just need to divide out by the repeats. So we have 4 S's. So that's going to be 4 factorial. We have 1, 2, 3, 4 I's. And we have 2 P's. Okay. And just 1 M, so that's fine. And no other repeats there. Okay, so plugging all that in using our factorial key. Okay, and I got 34,650 different arrangements of the letters in Mississippi. Okay, and hopefully that was pretty straightforward. All it is just using that permutations through repetition formula that we went over on that last slide. Sorry, neglected to write the 2 P's here. Okay. I can let right along here. All right, so this one looks a little different. Person walks from A to B to C, always traveling south or east on the street shown below. So this person lives in a kind of a scary neighborhood where the roads are the exact grid. All right, how many different routes are possible? Okay. So this problem's actually going to be quite similar to the one we just did. It's kind of disguised though. Okay, so overall we have a 9 by 9 grid here. Okay, and let's just treat this like, so we'll have north, south, east, west, like we're just looking at it like a normal compass there. And this person's always going south or east. Okay, so first direction the person has to go is from A to B. All right, so let's just think about one of these routes here. So it'd be 1, 2, 3, 1, 2, 3, 4, 5, 6. Okay, so that route is made up of a total of 9 blocks. Okay, this is from A to B. It's made up of a total of 9 blocks, with the 3 of them being south over there, and 6 of them being east. Okay, and the same thing would happen regardless what route we took. Even if we took, let's say we take this route here. Okay. Okay. Once again, you notice it took 3 souths and 6 east. So all of those routes between A and B, okay, are going to be that same pattern. Okay. And it kind of eliminates the issue that it's impossible because of the fact they're only going south or east. We don't need to just consider any of these odd routes like that. Okay, so we are set with just those that we've already gotten. Okay, so maybe you can kind of see here, this is going to basically can be some kind of arrangement. We can kind of think of this as a word with 3 S's and 6 E's. So we can use the formula that we just developed, okay? How many different permutations and how many different arrangement of those letters can we make with this E word that we just developed here, okay? Well, just following the formula, it would be 9 factorial, because that's the total number, divided by 3 factorial for the 3 s's, and 6 factorial for the 6 e's. So that would be 9. Okay, and so that would be 84 roots. Okay, and so that's just from A to B. So now let's do B to C. We can do very similar logic. All right, so let's kind of think about the roots from B to C. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so it's going to be 9 blocks once again. Okay, this time it's just 6 south and 3 east, but it's going to be very, very similar setup. Okay, just because the letters have changed here, it's still S, 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 E, E, E. Okay, and remember, all of those roots are going to be the same amount of souths and easts. So now we're just trying to figure out how many words we're going to make from this E. So it's going to be the same thing. They'll just be 9 factorial over 3 factorial times 6 factorial, which is the same exact thing we did up there, or 84 roots. So to figure out the total number of roots, all we got to do is just use that multiplication principle. It's going to be 84 from A to B, 84 from B to C, and you get a total of 7,056 roots. Okay, so this person can entertain themselves in quarantine, going for walks for quite a while. All right. So another kind of thing that from this section is called circular permutations. Okay, so far we've just been doing linear permutations, and linear permutations are the types of thing where it's like, how many ways can these people line up? How many ways can these people sit in these 3 chairs? Okay, if you notice in a circular permutation, it's a little bit different. Here we have these kind of arrangements of these 3 people, X, Y, Z. Okay, and so this first one, we have X up top here, and kind of going around the table clockwise, we'd have Y, then Z. Okay, each of these arrangements in a circle is the exact same. Okay, and both times, if we're thinking about X, to that person's right is Y, and that person's left is Z. Okay, same thing's happening here. Here's X, to that person's left is Y, to that person's right is Z. Okay, so these 3 distinct kind of things in a circular permutation, they're all the same. Okay, the corresponding linear permutations for these 3 people, if they were going to like line up in a line, these are all different, right? X, Y, Z, Z, X, Y, Y, Z, X. Okay, so we kind of have to think of a relationship to how we kind of figure out the relationship between the number of linear permutations and the number of circular permutations. So the number of linear permutations for these 3 letters would be quite easy. It's just going to be 3 factorial, which is 6. Okay, and we notice that for every 3, for those 3 linear permutations, we have 1 circular permutation. Okay, so we can just divide that 3 factorial by 3, and that would give us the corresponding number of circular permutations. Okay, so let's kind of just generalize that formula over here. Since each circular permutation may be written as a linear permutation in n ways, there are n minus 1 circular permutations. Okay, so just like we were doing over there, okay, for the people like 3 people in a circle, the linear could be written as n factorial. Okay, and we were just dividing that by n. In the other problem, it was 3 factorial divided by 3, which just gets us n minus 1 factorial. This got us 3 minus 1 factorial, which is equal to 2 factorial. Okay, so a quick example of using that. How many circular permutations are possible when seating 5 people around a circular table? Okay, it's very simple using our formula. Here, n is 5, so it's just going to be 5 minus 1 factorial, or 4 factorial, which is just 24. All right, that's all I got. Try to keep these videos somewhat brief. Hope you enjoyed. See you next time.